This is my trigonometry course. Today we're going to learn applications of radian units for the measure of angles. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class, we learned a new unit for the measure of angles. And today we're going to learn a little bit about why that new unit is useful. In my geometry course, we learned this little part of the circle is called an arc. And to find the arc length, we use this formula here. That's the actual length of that green part of the circle. What we do is we find the perimeter of the circle, which is the distance all the way around the circle. The special name we give for that is the circumference. So this is the circumference, and then we multiply by a fraction because we only want a fraction of that total circumference. And a complete rotation is 360 degrees, and we use the central angle to help us find a fraction of that circumference. So theta is the central angle. So we can come up with a slightly different formula if we're going to use radians for the measure of the angle instead of degrees. So notice we have the orange 360 degrees. If we're going to use radian units for the measure of the angle, then we simply switch to 2 pi, because remember, in degrees, a complete rotation is 360, but in radians, a complete rotation is 2 pi radians. So again, we take the total length around the circle, the circumference, and we multiply it by this ratio, and theta now is going to be measured in radians. But notice when we do that, the 2 pi's cancel out, and we're left with this formula down here. The arc length, or the length of some arc created by the central angle theta, is equal to theta times the radius. It's very important to understand that you cannot use this formula unless theta is in radian units. It doesn't work unless theta is in radian units. So notice that this formula is much simpler than this formula up here, and that's one of the benefits of using radian units. We also found the area of a sector. This gray part of the circle is called a sector. And remember, area measures the space, the two-dimensional space in that part of the circle. And the way that we find the area of a sector is very similar to the way we find the length of some arc in a circle. This green arc here. Instead of taking the total circumference, we take the total area, which is pi r squared. That's the total area of a circle. And we again multiply by the fraction, because we only want a fraction of the area of the whole circle. But now that we're using radian units, we're going to switch 360 degrees to 2 pi, and then those pi's cancel out, and we have this simplified equation for the area. So the area of a sector is equal to theta in radian units divided by 2 times the radius squared. Most important thing to understand is that you can only use this formula with radian units. Your angle has to be in radian units, so that's true for both of these formulas. So let's do some practice problems. It says find the length of an arc on a circle with radius 3 centimeters and central angle pi over 7. Now remember, we mentioned that when you write radians, you don't have to actually write the unit. You can write rad for radians if you want, and some textbooks do that. you'll see pi over 7 rad, but you don't really have to. So let's use our formula. The length of an arc on a circle is equal to the radius of the circle times theta, as long as theta is in radian units. So we have 3 is the radius, and pi over 7 is the angle. And you don't have to write the units when you do the math, but I'm going to write those units just so you can get a feel for why we typically don't write the units for radian measure. So notice I'm writing centimeters and rad for radians. We're looking for arc length, so our answer should be in centimeters. Do you agree with that? If that's the length of an arc on a circle, like you see here, the length of the green part, then our final answer should be in centimeters. So if our final answer is in centimeters, that means we can't have a radian unit here because our final answer would be in centimeter dot radians, but that's not really a recognizable unit for us. So that's why we typically don't write the radian units, because we don't want them in the final answer. So we want our answer to be just a length. So we're not going to write those radian units. Now it doesn't say to round off, so we can just leave our answer as 3 pi over 7 centimeters. So that's the answer for number 1. Okay, it says find the length of the arc on a circle with radius 4.5. So the central angle is 8 pi over 5, so that means radians. If we don't have a unit, then it's assumed to be radians. So the radius is 4.5, and the angle measure in radians is 8 pi over 5. And if we multiply 4.5 times 8 is 36. So we can say 36 pi over 5, and feet is our unit. Now, how did I know that feet was the unit? Well, because the radius is measured in feet, so the arc length must be in feet also. There's no reason for the unit to change. So now it's time for you to try. Go and attempt number 3, and when you come back, we'll do it together. Okay, we're back. So the radius is 2 meters, and theta is 16 pi over 9. So we get 32 pi over 9 meters. So if you got that one right, excellent. Okay, go ahead and try number 4, and when you come back, we'll do it together. Alright, we're back. So the arc length is r theta. R, the radius, is 8 inches, and theta is pi over 8. Again, this formula only works if theta is in radian units. If you write theta in degree units, it does not work. So we have pi inches. So there you go. Because the 8's canceled out. So if you got that right, good. Okay, so now we're going to move to the area of a sector. We found the length of an arc on a circle, but now we're going to find the area, that gray, the gray region in the circle. So the area is equal to theta in radian units over 2 times r squared. And this problem says find the area of a sector of a circle with radius 20 millimeters and central angle pi over 5. So the central angle is pi over 5 and the radius is 20. So now we just have to do the math. So there's a lot of different ways that you could simplify that. But probably the easiest way to deal with this is simply use your calculator to find an approximation. So push the pi button, and if you're using iPhone, that's pretty easy. If you rotate in landscape mode, pi is right in the center. If you're using a graphing calculator, you'll have to push the blue second button at the upper left, blue second button, and at the right it's going to have an upside down V. Push that button, and that's going to be the pi button. And then we're going to push divided by 5 and then enter. And you'll push the equal sign if you're using an iPhone. Then divided by should say answer divided by 2 and then enter. Then times 20, then the upside down V button at the right, and then 2 for a second power, and then enter. And we should write approximately equal to. It says to round to the nearest tenth, so we get 125.7. And this is area, so we're going to have square millimeters. So what that means is that we're measuring, we're determining how many little square millimeters can fit in the sector of the circle. Okay, so again, we're just using this formula here, which again only works when you're using radian units. It does not work if you use degrees. Find the area of a sector of a circle with radius 6.23 miles and central angle 6 pi over 7. So the area of a sector is equal to theta in radian units over 2 times pi r squared. Theta in radian units is 6 pi over 7, and the radius is 6.23 squared. So again, the easiest way to do this is to use the calculator. 6 times pi, and again, if you're using the a graphing calculator, a Texas Instruments, it's probably going to be a blue second button at the upper left, and then the upside down V button at the right, and that's going to give you your pi button. So 6 times pi and then enter, and then divided by 7 and enter, and divided by 2, enter, and then times 6.23, the upside down V button, 2, so it should say 6.23 squared, and then enter. Now if you're having trouble entering this into your calculator, then that's okay, because everybody has trouble entering this stuff into the calculator when they first use your calculator. You'll get used to the calculator as you move along through the curriculum, but everybody has trouble using their calculator if you know, when you first try to use it. So don't worry about that. It says round to the nearest thousandth, so we should have 258, and that is square miles, the nearest thousandth. Okay, so I want you to try number 7. You're going to use this formula and round to the nearest hundredth. So try number 7. When you come back, we'll do it together. Okay, we're back. So the area of a sector is equal to theta in radian units divided by 2 times the radius squared. Theta in radian units is 5 pi over 9. and the radius is 32 feet. And we can enter all that into our calculator. 5 times pi, enter, divided by 9, enter, divided by 2, enter, and then times 32 to the second power. A lot of students would ask, why don't we just enter all that stuff into the calculator at once? You can do that, but it increases the probability of error in some cases. So we get 0.61 if we round to the nearest hundredth, and that is square feet. So if you got that one right, perfect. Go ahead and try number 8, and when you come back, we'll do it together. Okay, we're back. So the area of a sector is theta over 2 times r squared, if theta is measured in radians. If it's not, then this formula doesn't work. You cannot use degrees with this formula. So theta in radian units is 13 pi over 8, and the radius is 2 kilometers. So in our calculators, we're going to enter 13 times pi, enter, divided by 8, enter, divided by 2, enter, times 2 squared, which is obviously 4, and we get 10 point, well, it says round to the nearest whole number, so we'll just say 10. 10 square kilometers. So if you got that one right, excellent. Okay, so we need to define some variables here. If an object moves s units on a circle, so for example, if an object moves this distance on a circle in a particular amount of time, and we call that time t, then v is defined as the linear velocity according to this equation here. So let's say you have a circle and something moves some distance s on the circle in a certain amount of time. Then you take that distance and divide by how much time it took to move that distance, and that gives us what we call the linear velocity. Linear velocity is just like miles per hour on the road, or it's how fast a plane is moving. It's just the basic idea of speed. And the word velocity, when you take a physics course, it has a deeper meaning. Mathematicians have chosen to use the word velocity because we're actually moving in a circular direction, so that kind of applies direction and speed. So whenever you have direction and speed, you use the fancy word velocity. But it's you can just think of it as speed. So this is the distance that we're moving, and this is the time it takes to move that distance. Divide them and you get the linear velocity. Okay, we also have something called angular velocity. If an object on a circle rotates theta angle units, so for example, let's say an object moves from here to here, and the corresponding angle that is mapped out or displayed, however you want to say it, is theta units. If we divide that theta by the amount of time it takes to move that distance, that's called the angular velocity. So the central angle that corresponds to that movement divided by the amount of time it takes to move that distance is called the angular velocity. So angular velocity can be measured in degrees per unit time or radians per unit time. And all the problems that we're going to be doing, we need to use radians. Generally speaking, you don't use degrees with any of these types of problems that we're doing today for various reasons. So if an object on a circle rotates theta angle units in t units of time, then omega is defined as the angular velocity according to this equation. Now, the big question obviously is, well, why do we care about that? Well, let's take the first equation. Linear velocity is equal to the arc length divided by the time. And let's now use the formula that we learned for the length of an arc. If you want the length of an arc, you multiply the radius by the angle measure in radian units. So again, remember we learned that formula in the first part of the class. The arc length is equal to the radius times theta, as long as theta is in radian units. So we're going to take this formula here and we're going to replace the arc length with r times theta, because again we learned that formula at the beginning of the class. So linear velocity is equal to the arc length divided by time, but if we replace the arc length with r theta, then we get this formula here. V is now equal to r times theta over t. So all we did was just move this r to the side a little bit. You don't have to do that. But remember, we just defined the rotation divided by the amount of time it takes as omega, the angular velocity. So we're going to change that theta over t to omega. And from that, we generate this equation. The linear velocity is equal to the radius of the circle times the angular velocity. This only works if the object is moving in a circular path. And it only works if theta is measured in radian units. If it's measured in degrees, none of these formulas that we're using today actually work. That's the most important thing to understand. So let's use that formula. V is equal to r omega. An object moves on a circular path with an angular velocity of 3 pi over 7 radians per second. What is the object's linear velocity if the radius of the path is 2 inches? So we know that V is equal to r times omega. The linear velocity is equal to the radius of the path, the circular path, times the angular velocity. We know that the radius is 2 inches, and we know that the angular velocity is 3 pi over 7. So that's it. We're done. The linear velocity is 6 pi over 7. 6 pi over 7 inches per second. Now, how did I know inches? Well, because the radius is in inches. How did I know seconds? Because the angular velocities is measured in radians per second. But notice that the radians kind of disappeared. That's why we don't need to write units whenever we state radians. Radians are not really a required unit. If we did write the unit, we'd have to say inches dot radians per second. Inches dot radians per second. We don't want to do that. We just want to write inches per second. So again, it's convenient to just not write the units for radians. You don't have to do that. And these problems demonstrate why. Okay, an object moves on a circular path with a linear velocity of 8 meters per minute. So now they're giving us linear velocity. What is the object's angular velocity if the radius of the path is 22 meters? So now we're going to go backwards. So we know that v is equal to r times omega. They told us the linear velocity is 8 meters per minute, and the radius of the circular path is 22 meters. And we're looking for omega. Actually, we don't really need parentheses. So omega is simply equal to 8 over 22, and we can reduce that to 4 over 11. We don't really have a lot of room, so I'll just reduce that there. So we have 4 over 11, and this is angular velocity, and again, remember, we only use radians when doing these problems, so we can say radians per minute. Now, how did I know per minute? Well, because it says the linear velocity is 8 meters per minute. But what happened to the meters? The meters just disappeared. Well, that's because there is no length in angular velocity. There's only an angle measure and a time. And when you're given the linear velocity and the radius of the pathway, and you use this equation to find the angular velocity, you're always going to get your answer in radians per unit of time. Now you might say, well, wait a second, I didn't think we had to write radians. Well, you actually don't have to, but sometimes it's convenient to write the unit. But if you wrote 4 over 11 per minute, then technically it wouldn't be wrong. We're just showing that this equation and these numbers produce radian angle measures. So go ahead and try number 11. That H stands for hours. So 15 pi over 8 radians per hour. So go ahead and try number 11, and when you come back, we'll do it together. Alright, we're back. An object moves on a circular path with an angular velocity of 15 pi over 8 radians per hour. What is the object's linear velocity? So we're looking for v. So the radius of the path is 12 feet, and the angular velocity is 15 pi over 8. And if we multiply, we get 45 pi over 2. And you can multiply 12 and 15, but when you divide and simplify, you're going to get 45 pi over 2. So our units are going to be feet, because the radius is in feet, and hours, so feet per hour, because our angular velocity is in radians per hour. So again, notice how the radians just kind of disappear. That's why radians are so effective. That's why we measured or we defined radians the way we did, because using these formulas, they just kind of disappear conveniently, the units. Okay, go ahead and try number 12. Number 10 will help you, and when you come back, we'll do it together. Okay, we're back. an object moves on a circular path with a linear velocity of 9 centimeters per day. What is the object's angular velocity if the radius of the path is 3 centimeters? So now we're going backwards. We're trying to find the angular velocity. We have the linear velocity is 9. The radius is 3 centimeters. And we're looking for the angular velocity. So if we divide both sides by 3, we get 3. And that's it. All we have to do is write our units. So it's radians per day. And how did I know it's day? Because we have days up here. So there you go. If you got that one right, perfect. Okay, so now we're going to do some problems that require us to convert rates. We talked about the angular velocity of an object on a circular path. But in the real world, angular velocity is not usually measured with radians. It's measured with revolutions. More specifically, revolutions per minute. In cars, you'll have what's called a tachometer gauge, which shows you RPMs, revolutions per minute. That shows you how hard your engine is working, and if you overexert your engine, you can actually damage the engine. So it's very important to know the maximum RPM in a car. Oftentimes people talk about red line. So the RPMs go up and up and up and up, and everything's fine, but if you get to what they call red line, that means that you're stressing the engine. So you don't want to do that. So it's important to understand that a revolution is one complete rotation. That's just a fancy word that means a complete rotation. So one revolution is equal to 360 degrees. And if we write that angle measure in radians, it's 2 pi radians. Remember, we learned in the previous class that 2 pi is a complete rotation. So this is very, very important for these types of problems. Let's try a practice problem. What we're going to do now is just learn how to convert rates. So we have the maximum revolutions per minute of a particular motorcycle engine. That's 13,000. So we're going to take that number, 13,000 revolutions in 1 minute, and we're going to convert. Now I could have written this number as 13,000 revs with a slash like that. You can write it like this if you want. But when you convert units, sometimes it's easier for students to write it in this way. And what we're going to learn right now is something called the factor label method for converting units. We learned this in my arithmetic course, but it may be a while since you took that course. So we're going to convert to radians per second. Right now we're in revolutions per minute. So we need to convert revolutions, and then once we're done converting revolutions to radians, we're going to convert minutes to seconds. So it's important to understand that we can do this using steps. So I'm going to convert from revolutions to radians. So there's 1 revolution in 2 pi radians. How do I know that? Well, it says up here, a revolution in a circle is just 2 pi radians. That's the angle measure in radians for one complete rotation. At that point, we're done. we've converted revolutions to radians, but we also have to convert minutes to seconds. Now the reason that I know that this is correct is because the revolution units cancel out. You want one unit to be on the top in the numerator of a fraction and the other unit to be in the denominator. That means that they cancel out. So now I'm going to multiply by another conversion factor, and this conversion factor is going to be 1 minute is equivalent to 60 seconds. So now you see that the minutes, they cancel out because there's a minute unit in the bottom and a minute unit in the top, so they cancel out. But seconds and radians, they do not cancel out, they're left. But that's good because that's what we want. We want radians per second. So at this point we're going to multiply everything in the numerators. 13,000 times 2 pi is 26,000 pi radians. And the bottom we have 1 times 1 is 1, and then 1 times 60 is 60. So we have 60 seconds. So it says round. We could write this. We could just simplify that, but let's use the calculator because it says round to the nearest whole number. So 26,000 times the pi button, enter, and then divided by 60, and we get approximately 1,361, and that's it. So that is radians per second. So what we did is we converted revolutions per minute to radians per second. We were given an angular velocity, and maybe we should write that so we know it's an angular velocity. Omega is equal to that. Again, it's angular velocity. Revolutions per minute, we changed it to radians per second. Very, very important. Now, why did we do that? Well, we did it because we can't use revolutions per minute in our equation. We need radians per minute or radians per second. Now, we can still use our formulas if we keep our answers in minute per minute units. But this particular problem just asked us to find radians per second, so we had to do a number of conversions. Now, we call this the factor label method because we have all these factors, conversion factors we call them, and we're labeling all the numbers. We labeled with minutes and seconds and radians and revolutions. So it's called the factor label method, and it helps us because these conversions are very difficult. They can be very confusing, but this method helps us to make sure that we're doing it correctly. So let's try number 14. Now we're going to go in the opposite direction. And by the way, this factor label method will be useful to you when you take physics courses or chemistry courses, especially chemistry courses. So you're going to use this in science curricula. So it says a bicycle wheel rotates at 10 pi over 7 radians per second. Convert this to RPM. So we're going to start with our number 10 pi over 7 radians, and you could write a slash with a second, but just to make it easier for us to see, let's write 1 seconds in the denominator. So now we're going to convert everything separately. So I'll start by converting the radians to revolutions. There's 2 pi radians in 1 revolution. Now, why did I write the radians in the denominator? Because the radians have to cancel out. These radian units have to cancel, and the only way they can cancel is if you have radians in the numerator and the denominator. So those cancel out. And then I'm going to, so what we did there is we converted from radians to revolutions. So now I'm going to convert from seconds to minutes, and I want the seconds in the numerator and the minutes in the denominator because, again, that'll ensure that the seconds cancel out. Again, that's how you know that you're doing this properly. It takes a little practice to get these problems down, but that's okay. So now we're ready to multiply. So 10 pi over 7 times 1 is 10 pi over 7. And then 10 pi over 7 times 60 is 600 pi. 600 pi over 7. And that's in revolutions. 1 times 2 pi is 2 pi. And then 2 pi times 1 is 2 pi. So this factor label method looks very confusing, but when you get used to it, it's really not that difficult. Okay, so now we're ready to use our calculator. We could simplify this expression, but it says to round to the nearest hundredth, so we're going to go ahead and use the calculator. 600 times the pi button, enter, divided by 7, enter, then divided by 2, enter, and then divided by pi, enter. Now, I know what you're thinking. You're thinking you may want to divide by 2 pi all at once. Well, if you do that, your calculator might misinterpret. So you want to divide by 2 and then press enter, and then divide by pi again and press enter. That's the safest way to do it. If you're using a graphing calculator, you can divide by 2 pi, but I would write parentheses around the 2 pi just to be safe. So we get 42.86. 42.86. And let's write approximately equal to, and the units are RPMs, revolutions per minute. Now we could say revs per minute, but generally speaking, when you write revolutions per minute, we just abbreviate to RPMs. Okay, so let's do one more of these problems using the factor label method. A Ferris wheel rotates 2,447 degrees per hour. So now we're actually writing an angular velocity in degree units. And we're not really going to convert to degrees because our calculations or our formulas that we learned today don't really work with degrees. We're only doing this to help you learn how to convert between the units. So we're going to convert this to RPMs. So we're going to start with 2,447 degrees in 1 hour. So then we're going to convert everything separately. So let's start with degrees. There's 360 degrees in 1 revolution. Again, a revolution is a complete rotation. So we're in degrees, so we have to convert to revolutions. And then we're going to convert from hours to minutes. So there's 1 hour every 60 minutes. Now, how do I know that I did this correctly? I know because the degrees cancel out. We have degrees in the numerator and degrees in the denominator. And also, we have hours in the numerator and hours in the denominator. And we're left with revolutions per minute, which is what they're asking for. So now we just have to calculate 2,447 times 1, and then times 1 again is just 2,447, and its revolutions, that's what's left over. 1 times 360 is 360, and 360 times 60, we can do that in the calculator if you want. 360 times 60 is 21,600 minutes. So we want to divide these two numbers. 2,447 divided by 21,600, and we get approximately 0.1. It says to round to the nearest tenth. So the units are going to be revolutions per minute, of course, but we can just say RPMs. So by now you should have a fairly good idea of how the factor label method works. It's a very useful method for converting units, and I know that this is intimidating. It's very intimidating having to learn this method, but if you get stuck, that's okay. You can go to the previous problems. So I want you to take a picture of this page here, and I want you to take a picture, well, you can use number 15, try number 16. You're going to start with 1,200 revolutions every 1 minute. That's what you're going to start with. And it doesn't matter if you convert from minutes to seconds first or revolutions to radians first. It does not matter. You can do it either way. So try number 16, and when you come back, we'll do it together. Okay, we're back. So I'm going to convert revolutions first. There's 1 revolution in 2 pi radians, and there's 1 minute for every 60 seconds. So we have 2,400 pi radians and 60 seconds in the denominator. 1 times 1 times 60 is 60, and 1,200 times 2 pi times 1 is 2,400 2 pi. So 2,400 divided by 60 equals, actually you can say 2,400 times pi equals, and then divided by 60 equals. So we get 125, and it says round to nearest tenth, so 125.7. And the units are radians per second. And we should put approximately equal to. So if you got that one right, excellent. I know that it works because the revolutions cancel out, and I also know that the minutes cancel out. So if you got that one right, good. Try number 17. you're going to start with this number in radians every 1 second. And you can convert radians to revolutions first, or you can convert seconds to minutes first. It doesn't matter. You can do it either way. Try number 17. When you come back, we'll do it together. Okay, we're back. So we have 82 pi over 7 radians every 1 second. And I'm going to convert, there's 2 pi radians in every 1 revolution. Maybe we'll make that a different color. And so I converted from radians to revolutions. Now I'm going to convert from seconds to minutes. There's 60 seconds in every minute. So I'm going to cancel out those seconds. And I'm going to cancel out the radians. Maybe I'll use a different color for that. Canceling out those radians. And so if we multiply 82 and 60, we get 4,920 pi over 7 revolutions. And 1 times 2 pi is 2 pi times 1 is 2 pi. So we have 2 pi minutes. Again, these units are left over. They don't cancel out. So now in the calculator, we want to enter 4,920. Multiply that by pi, and then enter, and then divide by 7, and then enter, and divide by 2, enter, and then divide by pi, enter. There's a lot of different ways you can write that in your calculator, or enter it into your calculator, but you must be careful. So that is 351.429. It says to round off to the nearest thousandth. RPMs, revolutions per minute. So if you got that one right, excellent. If you're having a little trouble with this factor label method, that's okay. Every student has trouble with this when they first learn it. But you're starting to get the hang of it. All we have to do is more problems. Try number 18. You can use number 15 to help you. Start with 65,000 degrees per hour and convert to revolutions per minute. Try 18. When you come back, we'll do it together. All right, we're back. So let's write our starting rate. We have 65,000 degrees every 1 hour. And we're going to convert from degrees to revolutions. And then we're going to convert from hours to seconds, actually hours to minutes. There's 60 minutes in 1 hour. So our hours cancel out, and our degrees cancel out. That's how we know that we did the problem correctly. And the leftover units are in our minutes and revolutions. That's what we're looking for, RPMs, revolutions per minute. So now let's multiply, and we get 65,000 revolutions. 1 times 360 is 360. And then 360 times 60 is 21,600 minutes. And now we want to divide those numbers. So if we divide, we get approximately 3 RPMs. So if you got that one right, good job. Okay. So now let's do some problems that are a little more challenging, because these problems are going to have multiple parts. It says the wheel of a car rotates at 208 RPMs. So they give us the angular velocity. Generally speaking, angular velocity is not written with revolutions per minute, but that's still an indication of the angular velocity. We're also told that the radius of the circular of the wheel, well, the radius of the tire, that is 1.2 feet. And what are they looking for? They want to know how fast does the outer edge of the tire rotate. So that's linear velocity. They don't call it linear velocity, but that's what that is. The actual speed that an object is moving around the circle, that's linear velocity, v. The angular velocity is the change in the angle in a certain amount of time. So if we start there and go to there, we take that angle and divide by that amount of time it took to create that central angle based on the movement of the object on the circle, and that's angular velocity. So we're looking for the linear velocity, and we want the linear velocity, well, it doesn't say exactly what units, so we can write any units we want. As long as we use, well, we're going to stick with the units that they give us, feet and minutes. So we know that the linear velocity is equal to the radius times the angular velocity. So we can just use the radius, 1.2, and then multiply by the linear velocity, which is 208 RPMs. The problem is this equation does not work with revolutions per minute. Remember, this equation only works when we have radian units for the angular velocity. So we can't do that. The first step of the problem is to actually convert, and that's why these are challenge problems, is because we have to convert from RPMs to radians. We have to convert from revolutions per minute to radians per minute. So we have 208 revolutions every 1 minute. We're going to convert to radians so we can use that formula. That's the most important thing to understand about this class, is you cannot use the formulas that we learned previously unless you have radian units. So remember, there's 1 revolution for every 2 pi radians. So we get 416 pi radians in 1 minute, or we can write 416 pi rads per minute. Because this angular velocity is in radian units, we can now use it to find the linear velocity, which is what the problem is asking for. So we know the radius is 1.2 feet, and we know the angular velocity is 416 pi, and the problem says to round to the nearest hundredth. So 1.2 times 416, enter, and then times the pi button, enter. And we get approximately 1,568.28 feet per minute. That's how fast the edge of the tire is actually moving. The actual amount, the actual distance that the edge of the tire is moving in a certain amount of time. Okay, so that was kind of a challenge problem because we had two steps. We're not allowed to use revolutions per minute in this equation. So we had to convert to radians per minute. Then we could use the equation. Okay. Remember, the equations that we learned today can only be used with radian units for your angle. You cannot use degrees. The equation just does not work. So, let's try another one of these problems. The Earth completes one rotation in 24 hours. So that just gave us the angular momentum, or excuse me, the angular velocity, not momentum. So omega is equal to 1 revolution. Maybe we should start by saying 1 rotation, because that's what the problem says. 1 rotation every 24 hours. That's angular velocity. But remember, 1 rotation can also be called 1 revolution. So it's just a lot of fancy words that mean the same thing. So we have the angular velocity as 1 revolution every 24 hours. If we want to, we can write it as 1/24 of a revolution per hour, but you don't have to write it like that if you don't want to. It's probably easier just to leave it the way it is there. And we also know that the radius is the diameter divided by 2, so 8,000 divided by 2 is obviously 4,000 miles. So we were not given the radius, we were given the diameter. Sometimes in problems you're given the diameter and not the radius. So we need to find the linear velocity. It says how fast does a person at the equator move relative to the center of the Earth? So it wants to know how fast the person is actually moving. So that's going to be linear velocity. We're going to use v is equal to r times omega. Problem is we can't use revolutions per hour for omega. We need radians per hour. So we have to convert from revolutions per hour to radians per hour. Now notice that this problem says how fast does the person move on the equator relative to the center of the Earth. Relative movement can be kind of confusing because the Earth is orbiting the Sun, which means that the Earth is actually moving. So when we talk about speed, it's always relative to something. We're actually moving very, very fast around the Sun, but we don't really think about how fast we're moving relative to the Sun. But the problem is even more complicated because the Sun is rotating around the center of the galaxy. The Earth is part of a star system that is part of a larger galaxy. So we're moving even faster relative to the center of the galaxy. And it may be true that the galaxy itself is rotating around something, and the universe may be rotating around something, so it gets pretty complicated. So that's why we say, how fast does a person at the equator move relative to the center of the Earth? So that just means how fast, if you're looking from the center of the Earth, how fast is that person actually moving on the surface of the Earth. So we first need to convert omega from revolutions per hour to radians per hour. So we have 1 revolution every 24 hours, and we're going to convert, there's 2 pi radians in every 1 revolution. And so we get, well, the revolutions cancel out, of course, and we get 2 pi radians in 24 hours. 1 times 2 pi is 2 pi, and 24 times 1 is 24. So now we can simplify, and we get pi over 12 radians per hour. So now that we're in radian units, we can use our formula for linear velocity. Linear velocity is equal to the radius times the angular velocity. The radius of the Earth we found is 4,000 miles, and the angular velocity is pi over 12 radians per hour. So we can use our calculator because it says to round to the nearest whole number. So 4,000 times pi, enter, and then divided by 12, enter, is approximately 1,047. And the unit is going to be miles per hour. So if you're standing on the equator, then you're actually moving 1,047 miles per hour. You might say, well, that seems pretty fast, and it is fast, but thankfully the atmosphere tends to provide a lot of friction for anything that enters. So if some rock in outer space enters our atmosphere, the air molecules will bump up against the object and cause a lot of friction, which causes heat, and it'll burn up the objects in the atmosphere. So generally speaking, you don't have to worry about getting hit by anything as the Earth rotates. Okay, so I want you to try number 21. Go ahead and take a picture of numbers 19 and 20. These are 2-step problems, so they're challenge problems. So go ahead and try number 21, and when you come back, we'll do it together. Okay, we're back. So we're given the angular velocity is 136 revolutions every 1 minute. And we're given the radius of the rock. The radius of the rock is 30, or the radius of the rope, not the rock. The radius of the rope is 30 inches. So first we need to convert from 136 revolutions per minute to radians per minute. So there's 1 revolution in 2 pi radians. So we get 272 pi radians, and 1 times 1 is 1. We have 1 minute. So we can write 272 pi radians per minute. And the last part of the problem, the final part, is where we're looking for the linear velocity. So linear velocity is equal to the radius of the circular motion times the angular velocity. So the radius is 30 inches and the angular velocity is 272 pi. And we want to round to the nearest whole number. So 30 times 272, enter, and then times pi button, enter, and we get 25,635 inches per minute. Okay, if you got that right, good job. Go ahead and try number 22, and when you come back, we'll do it together. Alright, we're back. So, the ball completes one rotation in 0.12 seconds, so omega is equal to one rotation in 0.12 seconds. But remember, a rotation is the same thing as a revolution. And we also know that the radius of the movement, the radius of the ball, is diameter times 2, so 9.5, or diameter divided by 2. Diameter divided by 2, so that would be 4.75 inches. So step 1 is to convert from revolutions per second to radians per second. We can't use revolutions in our equations. We have to use radians. Radians are the only unit that works. So we know there's one revolution in every 2 pi radians. So the revolutions cancel out, and we have 2 pi radians for every 0.12 seconds. So we just multiply 0.12 times 1 is 0.12, and 1 times 2 pi is 2 pi. So now we have our omega value in radians per second. Now we're going to use that to find the linear velocity. Linear velocity is equal to the radius times omega. The radius is 4.75 inches, and we're going to multiply that by 2 pi over 0.12. So 4.75 times 2, enter, and then times pi, enter, and then divided by 0.12, enter. And we get approximately 248.7 inches per second. So that's how fast the ball, the outer part of the ball, is moving. So if you got that one right, good. Let's try some more of these. A toy train moves on a circular track. It completes 5 laps in 1.5 minutes. If the radius of the track is 100 inches, how fast does the train move in inches per second? So the difference with this problem is now we're converting to inches per second, not per minute, but per second. So we're given the angular velocity is 5 laps every 1.5 minutes, but 5 laps is the same thing as 5 revolutions, just for your information. You don't have to write this extra part there, but it's good to know that those are just the same thing as revolutions. And the radius of the track is 100 inches. So now remember, we can't use revolutions per minute, so we have to convert to radians. You can't use any of these formulas that we learned today unless you convert to radians. So omega is 5 revolutions every 1.5 minutes. And we're going to convert. We know there's 1 revolution every 2 pi radians. So we get 10 pi radians, and the revolutions cancel out. 1.5 times 1 is 1.5 minutes. So that's minutes. So this is the angular velocity, and you could simplify this a little bit, but it's easier just to leave it like that. So now we're going to find the linear velocity. The radius is 100 inches, and the angular velocity in radians is 10 pi over 1.5. So 100 times 10 is 1,000, times the pi button, enter, 3,141.59, divided by 1.5, enter. So we get approximately 2,094.4. And the units are inches per minute. But we're not done. We found the linear velocity in inches per minute. We don't want that. We want inches per second, so this problem has a little extra thing at the end. So now we have to go to step 2, and we have to take that number, and now that we know we have to convert that, we might as well go back, and instead we can just write 1,000 pi over 1.5. So that's inches per minute. The problem is we don't want inches per minute, we want inches per second. So now we have to rewrite the linear velocity, and the reason we kept it in this form is because we're still not done with the problem. We're then going to multiply and change that to inches per second. There's 1 minute in every 60 seconds. The minutes cancel out, and 1,000 pi times 1 is 1,000 pi inches, and 1.5 times 60 is 90 seconds. Again, the orange minutes cancel out. So now we're ready to calculate. We have 1,000 times the pi button, enter, and then divided by 90, enter, and we get 34.91 inches per second. So we found the answer, the linear velocity in inches per second. So I want you to take a picture of number 23. You're going to do a similar problem. Try number 24, and when you come back, we'll do it together. Okay, we're back. She runs 3 laps in 16 minutes, so that is the angular velocity. 3 laps in 16 minutes. But laps are the same thing as revolutions. So we have the angular velocity, and we know the radius is equal to 38 meters. So the first thing we need to do is convert to radians per minute. We have revolutions per minute. We need radians per minute. So there's 3 revolutions every 16 minutes. And we know there's 1 revolution in 2 pi radians. So that's the conversion factor. So then we get 6 pi radians in 16 minutes. So that's omega. So now we're ready to find the linear velocity, which is equal to r times omega. R is 38 meters. Omega we just found. By the way, we can reduce that, so that reduces to 3 pi over 8. You don't have to reduce it, but it just makes it easier, I guess, to write. And we're not going to be done with the problem after calculating this, so let's try to get an exact number. 38 times 3 is 114. So we have our answer in meters, meters per minute. But we don't want meters per minute, we want meters per second. So we have to do a third part of the problem. So linear velocity is equal to 114 pi meters in 8 minutes. And we're going to convert that to meters per second. So there's 1 minute for every 60 seconds. Multiply those and we get 114 pi meters. 114 pi times 1 is 114 pi. And 8 times 60 is 480. The minutes cancel out and we're left with seconds in the denominator. And it says to round to the nearest thousandth. So 114 times pi, enter, and divided by 480, and then enter. So our final answer is 0.746 meters per second. So let's make sure that that's what they were asking for. It says meters per second, so we did it correctly. So if you got that one right, good. The only difference with that problem is that we had to convert to seconds, distance per seconds at the last step. Okay, let's do some more problems here. So it says that a pepperoni pizza sits on the center of a rotating oven. One pepperoni is 8 centimeters from the center of the pizza and moves 0.2 centimeters per second. Okay, so we actually have 2 pepperonis that we're going to consider. The first pepperoni moves with this inner circle, and the second pepperoni is going to move around a circle that's bigger. I'm not drawing the circle perfectly, but so we're going to need 2 linear velocities and 2 radiuses, or radii. So I'm going to say V1, the linear velocity of the first pizza, is 0.2 centimeters per second. And the radius of the circle created by the movement of the inner pepperoni, the radius is 8 centimeters. So again, we're considering two circular paths. The first circular path has a radius of 8 centimeters, and the second circular path has a radius of 10 centimeters. So V1 is equal to R1 times omega. Now, the angular velocity is the same for every pepperoni and every part of the pizza, because that, everything is connected. But the linear velocity is different depending on what part of the pizza you're talking about. If you're on the outer parts of the pizza, you're moving a lot faster, because again, the pizza is at the center of the oven. So the inner parts don't move very fast at all, but the outer parts move relatively more quickly. So the linear velocity, we're told, is 0.2. The radius is 8 centimeters, and we're looking for omega. So now we have to divide both sides of that equation by 8, and so omega is equal to 0.025 radians per second. How do I know that we're using seconds? Well, because we use that unit up there. And how do I know radians? Well, because this equation only works if we're using radians. So if we try to solve for omega, we're always going to get radian units. When we plug in the radius and the linear velocity, there is no angle measure that's involved. So the only way for this equation to be true is if we have radian units. If we come up with degree units, well, again, this equation doesn't work with degree units, so that wouldn't make any sense. So long story short, we did it. We answered the question. But we have to answer the second part of the question. We answered this part: what is the angular velocity of the oven? But they now say another pepperoni is 10 centimeters from the center. How fast is the second pepperoni moving? So that was part 1, and we know, well, we're looking for the second linear velocity. In centimeters per second, and the second radius, the radius of the bigger pathway, is 10 centimeters. So the linear velocity is equal to the second radius times omega, and again, omega is the same no matter where you are on the pizza. So second radius is 10, and omega, again, it's the same no matter what you're talking about. So we multiply and we get 0.25 centimeters per second. So we found how fast the second pepperoni is moving. That's part 2 of the problem. Okay, so let's try another one of these problems. A boy pushes 2 other children on a merry-go-round at the park. One child is 6 feet from the axis of rotation, and the other is 3 feet from the axis. If the child closer to the center is moving 8 feet per second, what is the angular velocity of the merry-go-round, and what is the linear velocity of the other child? Seems like a pretty complicated problem, but let's just write things down first. So the child closer to the center is moving with a linear velocity of 8 feet per second. So we'll say V1 is equal to 8 feet per second. And R1, the radius for the first child, the radius of the child closer to the center, that would be 3 feet. So now we can write V1 is equal to R1 times omega. V1 is 8, R1 is 3. Solve, and we get 8/3 radians per second. So that is the angular velocity. That's the first part of the problem. So now we're going to look for the linear velocity of the second child. The problem actually gave us the linear velocity of the child closer to the center of the merry-go-round. But now we're looking for the linear velocity of the child on the edge of the merry-go-round. So the radius for him is 6 feet. He's farther out. So V2 is equal to R2 times omega. Again, omega is the same no matter where you are on the merry-go-round. So we have 6 times omega, which is 8/3, and that simplifies to 16 feet per second. So he's moving quite fast, 16 feet per second, so he's having a hard time holding on. Okay, so I want you to take a picture of number 25, and you can use number 26 to do 27. Go and attempt number 27. When you come back, we'll do it together. Okay, we're back. So V1, we're told, is 3 millimeters per second, and R1 is 15 millimeters. So that's the blue paint. So we're looking for the linear velocity, and we're just talking about the circular motion of that blue paint. So we have 3 is equal to 15 omega. Solve for omega, and we have 1/5 of a radian per second. So we did it. We found the linear velocity of the sprocket. Now we're looking for the linear velocity of the orange paint, which is going to be millimeters per second. And we know the radius for the orange paint is 26 millimeters. So we're looking for the linear velocity of the orange paint, which is R2 times omega. Omega is the same no matter where you are on the sprocket. So we have 26 times the angular velocity, and we get, I think that would be 5 1/5, or you can write 5.2, it doesn't really matter. 5.2 millimeters per second. So if you got that one right, excellent. So again, there's 2 parts to these problems. Go ahead and take a picture of number 27 if you'd like, and number 26, and those will help you with 28. Go ahead and try number 28, and when you come back, we'll do it together. Okay, we're back. So we have the linear velocity of one of the test tubes. Generally, you put test tubes in these centrifuges. It's 1800 inches per second. And the distance from the center of the centrifuge, the distance that that test tube is 4 inches. So we're looking for the angular the angular velocity. So we have the linear velocity of that test tube is 1800, and the radius of the circular motion is 4. So the angular velocity is 1800 divided by 4, which is 450 radians. It must be radians because there's no angles here, and we assume that this equation only works for radians. Radians per second. So we found the first part of the problem. Now we're looking for the linear velocity of the speck of mud, and that's going to be in inches per second. So the distance of that speck of mud from the center of the centrifuge is 3.4 inches. And so the linear velocity is equal to the distance from the center times omega. And omega is the same no matter what part of the centrifuge you're talking about. So 3.4 is the distance from the center to the mud. And omega we found in the previous part of the problem is 450. So 450 times 3.4 is 1,530 inches per second. So the mud is not moving as fast because it's closer to the center compared to the test tube. So if you got those right, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and screenshot number 2 and number 3 and number 4, number 5, number 6, number 7, and number 8. But don't go before you get your homework. Remember, the homework is required for this course. Here's screenshot number 1 of the homework, and number 2, and number 3, and here's the answers. Be sure to get those answers. You want to make sure you do the homework correctly and completely. So get that homework done, and I'll look forward to seeing you in the next class.